Let's pick up a few slides before the end of last period. We started talking about each moment of and in our discussion of that mass property, we basically gave kind of a definition, a discrete definition that would be used in terms of CSG type modeling. So where we have blocks and cylinders and wedges and things like that, we have small volumes. The way you compute the first moment of volume is by taking one of those discrete volumes of V1, you multiply that times its X center of mass, and you add that to the next volume V2 plus its times its center of mass plus and all the way out till you get all of the volumes multiplied times their X or their Y or their Z location. And those are then equal to the total volume, V1 plus V2 plus V up to N, times a X bar, Y bar, Z bar, which is the center of mass. And so that's the definition of the first moment of volume if it were a discrete problem. If it is a free-form complex shape, then we generally talk about it in terms of a triple integral, where we have for the first moment of volume with respect to X is the total volume times the center of mass X location is equal to the triple integral of X dV, and the same for Y and the same for Z. We know this first moment in a slightly different way. How we normally have it presented is based on a centroid definition. And so in the math courses that we've gone through and things like that, we typically have X bar equal to the first moment of volume with respect to volume, and then similar equations for Y bar and Z bar. And so generally, we don't deal with that first moment equation. The thing that I want you to be thinking about as we're going through these slides is really kind of this last bullet. If the object is composed of simple shapes, how would you compute its centroid? Well, you're going to use not triple integration, you're going to use some type of summation of these simple blocks or cylinders or whatever it is. And once we get to the end of this discussion, we will focus in on using a discrete and even more basic approach to calculating all of the mass properties based on kind of a discrete approximation of each of these mass property components. So the center of mass by definition, different than the centroid, is based on its geometric center. These two coincide with each other if the density is uniform throughout the entire part. And so, again, here's a calculation for the center of mass, and the only difference from the previous centroid is it has a parameter in there, rho, for the density, and that rho could easily represent a function. It doesn't have to be a constant. a fixed number, a fixed density, it can easily be a function that represents the density changes through the composite body or
is it going to be like really quiet?
The part if it's non-homogeneous. So then we talk in terms of not first moment of volume, we leave that behind and move on to, again, a more common calculation, and that's the first moment of mass. It's really the total mass times the distance from the origin to the center of mass. And so as before, where we kind of talked about it in discrete terms, here again we're talking about it as if it were CSG objects, little mass shapes, and M1 times the center of mass x sub C1 plus a second mass times its center of mass, and so on and so forth. And this discrete approach, again, would be used if you were doing CSG, strictly CSG type modeling. If you have any kind of free-form modeling that's done in the CAD system, then we would generally, based on the mathematics that we've been taught in our calculus courses, we would think that the computer is in there doing triple integrals, where it's integrating across very small dx, dy, dz, or little volumes, and integrating the density function if the density is changing through the shape of the part. The moment of inertia, also referred to as the second moment of mass, its definition is pretty simple and straightforward, and we generally think of it in terms of IZZ. And so IZZ is what we're looking at here, and you take a simple mass element, you calculate its radius from some axis, some rotation point, and you determine what R is for that little mass element, and you do that over and over again, collecting up all of it's the summation of all of those little masses. If we're doing kind of the CSG approach, if we're doing a free-form shape, then we're going to use one of these integrals. We'll either integrate with respect to a small mass, or we'll integrate with respect to if the density through the object is changing, then we're going to do typically the bottom integral, the triple integral, where we can integrate the mass changing through the x, y, and z space, the three-dimensional space of the object. So that's for z. What is it for IYY? Well, all you do is get rid of the x squared component, the y squared component, replace it with z squared. If you're looking at the x, the IXX term, then it's just y squared plus z squared. And so it's a pretty simple set of equations to kind of remember and use in doing your engineering work. The products of inertia, generally we think of the products of inertia as kind of the out of balance products. So these are the products that typically are going to cause a imbalance in the system. For those of you that have purchased tires for your cars and had the tire shop put the new tires on the rim, after they put the tires on the rim, they take the rim and tire over to a balance machine and they spin the tire up, and what they're looking for are the products of inertia, the out of balance of the wheel, and then to try and get the products of inertia to be zero, they add weights to basically force the imbalance to move off that axis and be located back at the center of either the IXX, IYY, or IZZ axes. And if you drive all of the products to zero, all you have are the moments of inertia, which would mean your system shouldn't ever become unstable. It should you shouldn't have any wobble or any vibration that's being introduced to the system. And so generally, in doing any CAD design of parts that rotate or parts that move freely in a system, you're going to want to make sure that their products of inertia are as close to zero as possible. The principal axes, basically the orientation that produces zero products of inertia. And so when they're spinning that tire around trying to find the places to add weights, what they're generally trying to do is figure out where to mark the tire. And in marking the tire, they're actually locating one of these principal axes to try and add weight or adjust the weight to drive the products to zero. The way that you typically solve for the principal axes, which again they do in the calculus math courses and in some of our physics and engineering classes, is they set up the angular momentum equation, and in coming up with the characteristic equation, which is basically developing an equation along the diagonal of this matrix, they then solve that characteristic equation both for the values as well as the vectors that drive this system, so that it's basically kind of a values strictly down the IXX, IYY, and IZZ, the diagonal terms of that tensor. So that's the mathematics that are kind of behind, or what we think are generally behind, the CAD system. When the CAD systems were in the early stages of development, they had very simple primitives or very simple shapes that they could do match properties on, and it was typically using the summation approach. As they improved kind of the mathematics and they built the mathematics into the CAD system, they started doing the integration or the numerical integration to those systems, to those calculations, because they became much more accurate. They could drive the discrete volume, the little dx, dy, dz, they could basically drive that to as small as they wanted. And by getting smaller and smaller size,